Welcome back. In the last couple of classes, we extensively discussed proton NMR spectra, analysis of proton NMR spectra, carbon 13 NMR spectra, its analysis, and editing of the carbon 13 spectra based on the number of protons attached to different carbons by carrying out experiment called depth 90, depth 45, depth 135, like that. And we discuss a lot about varieties of chemical shifts possible and how we can assign the carbon spectra based on chemical shifts. And I discussed, as I said, the factors that affects the chemical shift of protons also affects the chemical shift of carbon. That's what I said. Okay. Now let us continue today. Little bit deviating from heteronuclear carbon 13, some heteronuclear interactions. And I want to just give you a brief idea about various possible couplings we can think of. For example, among heteronuclear couplings, they can be very, very large. For example, take an example of a one-bond coupling between thallium-205 and carbon 13. If you consider, it can vary from 2 to 10 kilohertz. Remember, 10 kilohertz. In fact, in some of the nuclei like carbon 13, etc., it will cover almost half the spectral width. In a 500 megahertz, carbon 13 will be about, let us say, 30,000 hertz or 35,000 hertz is the spectral width. Nearly one third of that or half of that spectral width is of the order of J coupling here. In exotic nuclei like this, sometimes chemical shift range will be very large. For example, in nuclei like cobalt and others, if you go, chemical shift can go up to 65,000 ppm. It is really large. Similarly, couplings can be quite large in cases like this. For example, thallium to carbon 13, 3-bond coupling can be of the order of 1 kilohertz. Quite large. For example, 1-bond tin proton is very small, and tin to tin coupling can be there. Remember, tin has 2 isotopes. We will discuss as we go ahead further. That can have coupling of the order of 4.267. We can even detect the coupling between 2 dilute spins, whose abundance are very small. They are called dilute spins also. So we can see that in one example, the mercury-mercury coupling, mercury 199 to mercury 199 in this type of ion is 139 kilohertz. Imagine, that is J coupling I am talking, not the chemical shift, not the spread of the spectral width. It is 139 kilohertz is the J coupling. So just to give you an idea, heteronuclear interactions, heteronuclear couplings can be substantially larger. So that's what I wanted to tell you in this class, and I wanted to give you a few examples. In the case of platinum, I consider a system like this: phosphorus platinum X. We can look at the platinum to phosphorus coupling. See, phosphorus has been half nuclei. So if I look at that, the coupling between phosphorus and platinum, when X substituent, depending upon the substituent, if it is chlorine, it can be of the order of 4.26 kilohertz. And if it is X is CN group, it is close to 2.9 kilohertz. That is the order of coupling. Heteronuclear coupling, see, so far we were discussing about proton and carbon, where the coupling constant is of the order of few hundred hertz, in case of proton few tens of hertz. But when you go to exotic nuclei, some of the rare nuclei or some other heteronuclei, they are so exotic, the coupling constant can be of the order of several kilohertz. This point you have to keep in mind. I just want to give you another example. You take the methane. Methane has carbon proton coupling, which, as I told you, you will not see it in either carbon spectrum or proton spectrum. Okay, carbon spectrum, I would say, if I take carbon 13, I will see it. I take back my sentence, you will see that. In the case of the proton, you will not see proton-proton coupling. CH coupling you will see, but it is very weak. It is a satellite. Now, in the carbon-proton coupling, if you want to see in it, this CH4 group, it is of the order of 125 hertz. This is what I said when we discussed about the carbon-proton couplings. Now, the same thing is of CH4, take SiH4. Now, proton to silicon coupling is about 200 hertz and it has a negative sign, because silicon 29 has negative magnetic moment. All the nuclei which has negative magnetic moment, their signs of the coupling you have to represent as negative sign. For example, 1 bond nitrogen 15 proton coupling is 90 hertz. Many times people write 1JNH equal to 90 hertz. In principle, you have to write as 1JNH equal to minus 90 hertz because nitrogen 15 has negative magnetic moment. Similarly, in this case, for example, silicon has this one. Of course, sometimes even in the when two nuclei with positive gyromagnetic ratio also can a negative sign, that's a different question. I took this example of silicon because I know silicon 29 has negative magnetic moment. Look at germanium, instead of CH4, if I get GH4, it is 98 hertz with negative sign. On the other hand, if it is SnH4, it is close to 2 kilohertz. See, these are the things which I wanted to point out to keep it in mind. So now what we will do is, we will understand how to get the coupling between different abundant heteronuclear spins, how we can observe. Take a molecule like this. Now, there is one fluorine here. Of course, we saw that in the fluorine proton coupling everything earlier, but again, I want to brief it to you. You can get coupling between proton and fluorine, both are heteronuclei, but both are spin half, both are abundant almost 100%. Proton is 99.98, this is 100%. Take it, both are 100% abundant. Now, if fluorine is substituted in this molecule here, you can easily get coupling of this fluorine to this one, coupling of this fluorine to this proton, coupling of this fluorine to carbon. If you look for the carbon NMR, all couplings can be visible. The coupling strength of fluorine to proton can be 2 bonds, can be 3 bonds, and you can see everything. Okay. So, if orthofluorine proton coupling, if you have to see, this is generally of the order of 8 to 10 hertz. And meta is about 1 to 3 hertz. Exactly similar to proton. See, in the phenyl ring, I told you, proton-proton ortho coupling is about 8 to 10 hertz. It can be 7 to 8, 10 hertz, let us say. And meta coupling, I said it is 1 to 3 hertz. Exactly here. Just by substitution of the fluorine, the coupling in this type of rings do not change much. Similarly, here, if you look at this, this one, this is for proton 4. If you look for this proton 7 here, we have an ortho HH coupling and we also have a meta FH coupling here. This experiences 2 heteronuclear coupling. One, of course, homonuclear and one heteronuclear. 2 couplings it is experiencing, both homo and hetero. Okay, same here also. Proton 4 experienced both homonuclear and heteronuclear couplings. So like this is like analysis of the proton spectrum. More or less like, we analyze the proton spectrum looking at this type of pattern, because there is not much of a difference here, especially in ring system like this, between proton and fluorine. The couplings are more or less similar to proton-proton couplings. Here again, if you look at the proton 6, it experiences ortho FH coupling, ortho HH coupling, and meta HH coupling. All the 3 couplings are expected here. See, that's why this has a funny pattern like this. We can interpret that and easily analyze. I just wanted to show you how we can analyze the spectrum. For example, you would look at this proton 4. Ortho coupling is about 10 hertz. Okay, it's a large doublet. And then it is also experiencing the meta coupling, which is about 2.7 hertz. So it's doublet of doublets. And what about para coupling? It is there, but you're not seeing it. It is very weak, so you don't see it. Now coming to proton 7, ortho coupling makes it a doublet, and meta coupling between fluorine and proton is about close to 4.7 hertz. So it's a well resolved doublet of doublets. So analysis of this type of spectra when proton and fluorine are coupled is fairly simple. It's not that difficult. Okay. So you extend this. If I look for a molecule like this, you have 2 fluorines and 1 fluorine here. And if I look at this fluorine, what is going to happen? It is coupled to 2 fluorines almost equally because of the perfect symmetry. They are chemically equivalent. Coupling is also same. Then it will become, instead of doublet of doublet, central line of the 2 doublets overlap. It looks more like a triplet. Interesting, right? It looks more like a triplet. Interestingly, these 2 protons are also coupled to this with the same equal coupling strength with this proton to this fluorine and this proton to this fluorine. Meta couplings between proton and fluorine are both equal. Again, it looks like a triplet pattern because couplings are equal. Central lines of FH couplings also overlap. So what you are going to see is triplet of triplet for this fluorine. Very clear. So interpretation is not difficult. I hope you are all with me. Just to make you understand, I'll repeat once again. Look at it. This fluorine is chemically inequivalent compared to these two fluorines. There is a perfect symmetry for this molecule. So this fluorine and this fluorine are chemically equivalent. At the same time, the coupling of this fluorine to this fluorine to this are also equal. It means if I look at the splitting pattern of this fluorine, should be doublet of doublets. Because both the couplings are equal. We remember we worked out the multiplicity pattern. When both the couplings are equal, central lines of two doublets, both lines overlap. As a consequence, it appears like a 1:2 to 1 triplet. Exactly, it appears like 1:1 triplet. Similarly, this proton and fluorine coupling, these two meta couplings are also identical, and they also are coupled to this fluorine. As a consequence, again, it looks like a triplet. So each chain of this triplet is further split into triplet of triplets. Each chain is a triplet. So it is going to be triplet of triplets. Now on the other hand, this one, they are equivalent. If you treat like a single fluorine, so it will couple with this fluorine and becomes a doublet. And again, it will couple for these two fluorines, these two protons, which are equivalent. Again, it is a doublet. So it is going to be doublet of doublets. You understand? What is the largest coupling is between these FF coupling. It is about 19.84, and this meta coupling is about 6.17. As a consequence, it appears like doublet of doublets. Are you all with me? This is easy to understand, very easy to interpret the spectrum. It's a very simple molecule. We have heteronuclear couplings and homonuclear couplings also between abundant spins. But the only thing is FF coupling you don't see. I'm sorry, you see in the proton NMR. This is, I'm sorry, I'm looking at fluorine. Fine, you see. If you see the HH coupling between them, that you don't see, because we are looking at fluorine NMR. That is what you should understand. Now I look for another example where two abundant spins are coupled. Okay. So what is happening now when two abundant spins are coupled? Look at what are the two abundant spin? Phosphorus and proton, both are abundant. Let us look at the 31p spectrum of this molecule, a complex. How many types of phosphorus are there here? This is one phosphorus, this is one phosphorus, and this is another type of phosphorus. Because there is a perfect symmetry along this axis, it's a square planar. So now what I'm going to see is this phosphorus and this phosphorus are chemically equivalent, and this phosphorus is different. If I see phosphorus spectrum of this molecule, how many peaks I should expect? I must expect lot of peaks. Remember, first phosphorus coupling is seen, and phosphorus proton coupling can also be seen. To simplify the spectrum, what is done here is protons are decoupled. Remember, I explained to you the carbon 13 NMR. We can completely remove all the couplings of protons to all carbons by broadband decoupling. Exactly, you can do this. I said at that time also, this type of broadband decoupling is not restricted only to carbon 13. You can do this for any nuclei of your interest. Now we are observing phosphorus decoupling all protons coupled to it. So now we are seeing only there is no proton phosphorus coupling. If at all we see only phosphorus coupling. This also will not couple. Okay, this is a metal. It's a different question. So how many peaks you expect? 2 peaks. These two are equivalent. One phosphorus is another phosphorus. Very nicely you can see. But now you understand the pattern. This phosphorus is a doublet. Why? This phosphorus, they are equivalent coupled to this phosphorus. So this phosphorus makes these two as a doublet. It is like CH and CH2. CH coupled to CH2 proton. So CH2 will be a singlet, right? Similarly, the two equivalent phosphorus is a singlet. On the other hand, if I see this phosphorus, it experiences equal coupling between these two phosphorus. Like CH proton coupled to CH2. What do you expect? A triplet. Exactly. This phosphorus is a triplet because of these two phosphorus couplings, and this phosphorus, these two are doublet because of this coupling to this phosphorus. So these two are chemically equivalent, and center of this gives you chemical sheet of this phosphorus, center of this gives you chemical sheet of this phosphorus. What happens if I see the proton NMR of this? That is interesting. Proton NMR, if you see, what happens? This is coupled to this is coupled to this phosphorus, and makes this a triplet. But at the same time, this is also coupled to this phosphorus. You may be wondering what happened to a phenyl proton, that is far away, and there is a long range coupling, you will not see. But this phosphorus can split to this. So it will be first a triplet, or okay, this will make a large doublet because the HP coupling is larger, and each line of this doublet is split into a triplet because of these two phosphorus, equivalent phosphorus. This is the proton NMR spectrum. Is it clear for you? Now I'll bring in another concept called satellite analysis. What is a satellite analysis? We'll understand this more now. Let us look at the proton spectrum of CHCl3, not carbon 13. I am asking for proton spectrum. Remember, when I analyze the spectrum, and I told you for a single spin nuclei, when I was analyzing the spin system, I said it will give a single peak, proton. True, no doubt about it. When I see carbon 13 spectrum, I see a doublet. Because CH carbon will be a doublet, I told you. Remember, when I analyze carbon spectra, I said CH3 will be a quartet, CH2 is a triplet, and CH carbon is a doublet. Correct. If I see carbon spectrum, it is a doublet. And if I see the proton spectrum, it is a singlet. How is it possible? Remember, I also said interactions in NMR are mutual. So when proton is coupled to carbon, carbon is also coupled to proton. Then the question is, why proton spectrum is not a doublet? Why only carbon is a doublet? The answer to this question lies in understanding the isotopomers. You understand? You have to see what are the types of isotopomers you see. Carbon 13 has two isotopes, carbon 12 and carbon 13. This abundance is 1%, as I have been telling you. This abundance is only 1%. So if I take 100 molecules of CSCl3, only one molecule is carbon 13. Remember, in the 13th spectrum analysis, I discussed this in depth. We extensively discussed this abundance factor. So it will be one molecule will be in the existing as carbon 13. 99% or 99 molecules among 100 molecules will exist as carbon 12. And what you see in the proton spectrum corresponding to 99% of the molecule which are attached to carbon 12, C12, HCl3. What is the magnetic moment of carbon 12? Spin is 0. So there is no magnetic moment. So this cannot couple to this proton. As a consequence, you will see only one single peak. But why did we see doublet in carbon 13 NMR? Because we are directly looking at the carbon 13 isotopomer. In the proton, it is a mixture of both carbon 12 and carbon 13 isotopomer. Remember. So in the proton NMR, we have mixture of isotopomers where largest peak intensity correspond to this isotopomer. And what happened to 1% of carbon-13? That is present. And that splits because of carbon-13 into a doublet. You see, you take the proton and NMR spectrum of CaCl3, enhance the intensity. You are going to see two peaks, chota peaks on either side. It is equidistant on C. Of course, most of the time it will be equidistant, but there is also called isotope effect. I will discuss later. As a consequence, it need not be, small difference could be there, but generally they are equidistant on this central peak. But what is the intensity of it? This is 99%, but this is only 1% carbon. But that carbon is coupled to proton. What will happen to intensity of the peak? It will divide itself into two because there are now two peaks. So one peak became two. Remember the splitting pattern I explained. The intensity now reduced to half. So what happens? Carbon-13 intensity is only 0.5% compared to 99% of carbon-12. It is very, very chota peak. That is why these are called satellites, small peaks. Whenever you observe an abundant spin, if it is coupled to a low abundant spin, abundance of the order 1% or 2% or 5% like that, then that coupling appears as satellites. Major peak is because of other isotopomer, and satellites will come because of coupling to a low abundant nucleus. Okay, now carbon-13 abundance is 1%, and you got a doublet because of carbon proton coupling with intensity of 0.5 and 0.5. Hence, these are called satellites. Remember that. Okay. And this separation gives me coupling between proton and carbon. If you go to carbon-13 spectrum and get the carbon spectrum coupled, not decoupled, carbon coupled spectrum with proton, you get the same doublet with the same separation. Then there also you can get J coupling. Here also you can get J coupling. You understand? This is what it is. So what I said, interactions in NMR are mutual is true. It is valid. See here also you can see the coupling. You can also see in carbon NMR. But why I said I posed the question we are not seeing is because of this isotope. Okay, that's the point. Please remember this point. Now, this type of satellite analysis I want to show you with one or two more examples. For example, look at tetramethylsilane. Now, abundant spins are protons. Carbon is 1% abundant. Silicon is also about 4% abundant. Okay, very small percentage. Now, where we should see silicon? We should see them as satellites. This is now, if I look at the proton and NMR spectrum of tetramethylsilane, now larger component is of the proton comes because of carbon at 12 attached to protons, this one. And carbon-13 coupled to proton appear as satellites here. The silicon-29 can also couple to proton. That is also because of less abundance appear as satellites here. You can see that. You can see that as satellites. This peak and this peak, which is about 6 Hz separation, is silicon proton coupling. Is 1 and 2 bond coupling is there. So 1 bond CH coupling is 110 Hz, and 2 bond silicon proton coupling is 6.6 Hz. But it may so happen. Remember, I was telling you, in the carbon-13 NMR, this carbon can also couple to this proton when I see the coupling. So this 1, 2 and 3 bond proton carbon coupling also can be seen. There is only one such possibility. All are equal. If I see this carbon, this is 3 bond. If I see this carbon, this is 3 bond, this is 3 bond, all are 3 bonds away. So there are 2 types of carbon couplings here. Carbon proton, 1 bond carbon proton close to 119 Hz, and 3 bond carbon proton close to 1.9. As you see, you can see here, very weak in intensity. And these are called satellite peaks. But you can analyze them. You can't ignore them. So you can analyze. If I analyze this, measure the separation, I can get the J coupling between carbon and proton. I can measure one bond coupling. I can measure this separation. I can get two bond silicon proton coupling. I can measure this separation. I get three bond carbon proton coupling. So though the satellites are there with weak intensity, you acquire a signal, enhance the intensity to a larger height, and then look for this satellite peaks. You can analyze this. This is called satellite analysis. You can do that and get the coupling information. Okay. So now I am asking you a question like this. Look, this is a paraxylene. Paraxylene, if you look at it, we have ring protons, one peak, all are equivalent. We have two CH3s, but they are chemically equivalent, giving rise to a single peak. Now, look at this proton. If you enhance the intensity largely to a higher, increase intensity by 3 to 4 times or 5 times, 10 times, this chota peak starts coming up. The small intensity peaks, they start coming up. What are they? They are carbon-13 satellites. Why is it a doublet? Because this carbon is coupled to, you are observing proton. This proton is coupled to this carbon. As a consequence, this CH3 peak is a doublet. This proton peak becomes a doublet due to coupling with carbon, spin half, and we got the doublet. Measure the separation, what you get? J carbon proton coupling. You ask me a question, why did I not see the same thing in ring? Of course, if you see the case carefully, if you do the experiment, acquire signal for a long time and enhance intensity, you can measure CH coupling for this ring carbons also. But I don't want to disappoint you. If you carefully see, you see a peak here. Okay. If you carefully see, you see a peak here and this peak. If I enhance the intensity a larger, I will see the satellite, this coupling, this separation correspond to carbon proton coupling here. But this is not a good spectrum since we are not acquired for a longer duration, so you don't see it. But if I acquire signal for another half an hour, then you will see satellite like this for this carbon also. You understand? So with this, now satellite analysis is becoming very clear for you. This satellite need not be restricted to only carbon. I said carbon is there, silicon is there, mercury, any of the low abundant spin can give rise to satellites. Now in this molecule, if you look for the fluorine NMR, how many peaks you expect from fluorine? There is a perfect symmetry, all fluorines are equivalent. As a consequence, you get only one peak for fluorine, we got only one peak. But what are these two peaks coming on either side? Extra peaks. This is because they are coupled to, this is a coupling to mercury. These 6 fluorines are coupled to mercury. As a consequence, what you are seeing is 1 and 2. 2 bond mercury 199 fluorine coupling. See? And this intensity is quite large compared to carbon 13 satellites. Because carbon is only 1%. So mercury is abundance is much better than carbon. As a consequence, this intensity also is better. Please remember this point. Only for carbon we got so weak intensity because of less abundance. You should not expect the same for all satellites. It depends upon abundance of coupled nuclei. So in this case, mercury abundance is much better than carbon. So satellite peaks are reasonably good to analyze. Now I look for the homonuclear couplings in the satellite spectrum. Now the question is, if I analyze the satellite spectrum, what do I get? I'll tell you, if I analyze the satellite spectrum, some information which you cannot get in the proton spectrum will get. And we did solve this in one example. I don't know whether you remember, in the spin system analysis of AA prime X coupled spin system, using Popel nomenclature, I showed you how to distinguish cis and trans isomers. Remember, where I showed you proton spectrum gives a single peak. Taking carbon 13 into account, you will break the symmetry, and the satellite peaks we got for cis and trans. One has a larger coupling, other has a smaller coupling too, and identified cis and trans. I hope you are all with me. Please don't forget. Keep following me regularly. That I discussed there. Exactly, you can do that. If you analyze that, you can get the homonuclear coupling, which you normally cannot get in the proton spectrum. Look at this one. This is a case of tetrabromoethane 1122. Now this proton and this proton are chemically equivalent. It's like a A2 spin system. So what can you get here? If you take the proton NMR spectrum, you are going to get a single peak. But if I want to find out what is the coupling between this and this, how do I find out? I told you this is a A2 spin system. That's why I introduced spin nomenclature. Remember, before we came to analysis. Now I consider this carbon in the state of carbon 13. If this carbon exists as carbon 13, now it is no more A2. Symmetry is broken. Then what do you call it? Because the coupling exists, now it is A prime coupling. They are chemically equivalent, but coupling also exists. Now it will become AA prime X coupling. Why I call it AA prime X? Because AX coupling and A prime X couplings are different. So it cannot be A2 now. It has to be AA prime X spin system. And this we analyzed earlier. Now what I do is, forget about this is a olden type experiment. They were spinning the sample and used to get some artifacts because of inhomogeneity of the magnetic field. We will worry about it later. I'll discuss when I come to practical applications. So now these are the satellites. What is now it is enhanced, plotted with the enhanced vertical intensity. What this separation gives you? This separation from center of this doublet to center of this doublet, what do you get peak on either side? This is one bond CH coupling. Remember, it is one bond CH coupling. And why each of them is a doublet? It is because it is 1, 2, 3 bond HH coupling. Remember, I am observing proton. So this coupling is seen and this coupling is seen. Both are seen. So we are going to see 3 bond proton-proton coupling in the satellite. So satellite analysis gives me homonuclear coupling among chemically equivalent spins, which are not possible to get from the regular one-dimensional NMR spectrum. So what we did is, we did not do anything for this thing for the molecule. Only thing is, we took the NMR spectrum and started looking for the carbon 13 satellites. As a consequence, we know the symmetry of the molecule is broken, and A2 spin system will become AAX spin system here. Analysis gives me CH coupling, HH coupling, both. This is another example. Same. Now, instead of the previous molecule with bromine substituted, tetrabromoethane, now it is SI2H6, this molecule. Here, no carbon. But what we can see? We can see SiH couplings and also HH couplings. Look at this one now. This silicon has spin half nuclei, is 4.7% abundant. When I do this proton NMR, I get a single peak. Coupling to silicon are only 4% intensity because they are satellites. And that is seen because only 4% of the molecule are present as silicon 29. But if this separation to this separation gives me what? One bond silicon proton coupling. Center of this quartet to center of this quartet. If I measure, I get one bond silicon proton coupling. At the same time, If you look at this one, what is this we are getting? This is HH coupling. This proton is coupled to this because now you have broken the symmetry. This methyl, this CH3 group and CH3 group are not same. When I consider the silicon, they are different. So this can split this, or this can split this. As a consequence, now these equivalent protons are split by CH3 group or SI3 group into a quartet. So satellite are appearing like a quartet. You analyze this, what you get? 3 bond proton proton coupling. This is 1 bond, and of course, if you carefully see, you can see 1 and 2 bond SH couplings also here. But some peaks are hidden here. Okay, because this also has to be a quartet, but it is hidden here. You can see 1 3 3 1 is hidden, so you will not be able to extract clearly, but it is there. All couplings information can easily be extracted. You understand? You got the point. How to analyze the satellites, everything. How we analyze the satellite spectrum to derive the information which is not possible to extract from proton spectrum. Okay, I am going to stop now.